Welcome, everyone. Thank you so much for joining us today for the Grasp on Robotics talk series. I'm Dr. Andrew Head, and I'm the faculty host for today's seminar. A quick reminder is that previously recorded talks can be found on the Grasp YouTube channel and website. And you'll also have an opportunity at the end to ask questions. And if you have a question during the talk, just raise your hand and I can come by and we can hand you the microphone so that you can ask it. So today we have an exciting special edition talk that's co-hosted by Grasp and Penn Human-Computer Interaction. Speaking today is Dr. Parastoo Abtahi. She is an assistant professor at Princeton University. There she leads the Situated Interactions Lab, which builds interactive technologies that extend human abilities and augment our intelligence situated in the physical world, drawing on an understanding of human perception and cognition. Within my circles, the kind of work from Parastoo's group is some of the most exciting to see demonstrated because as you use it, you feel your own abilities within the physical world actually get amplified. Parastoo's most recent work in this space is as a lab lead, and it draws upon an exciting repertoire that she developed as a PhD, a student at Stanford, and then as a visiting research scientist at Meta Reality Labs. She's been recognized as a Google Research Scholar, and she's also received numerous paper awards, including a hot off the presses Best Paper Award just 3 weeks ago at one of the top conferences in our field, WIST. So without further ado, please join me in welcoming Parastoo.
Great. Thanks so much, Andrew, for the introduction. Can everyone hear me in the back? Is the audio okay? Perfect. Great. Yeah, as Andrew mentioned, I'm Parastoo Abtahi. I'm a faculty at Princeton Human-Computer Interaction Group. So the caveat here is that I'm not a roboticist. I work in human-computer interaction, in augmented reality and virtual reality. But as you see, a lot of what we do intersects with human-robot interaction using robot for haptics in virtual reality. And so hopefully it's of interest to folks here. So when I started my PhD, it was around 2016, 2017. There was a lot of kind of excitement around virtual reality. There was Meta was coming out with, there was Oculus, and Meta was coming out with headsets around then. There was the HTC Vive. And so even though VR was around for a few decades at that point, it was an exciting time to be doing VR research because of all the commercial momentum that was existed at the time. So I always like to start off with kind of applications of VR that I find exciting, because usually people think of VR, they think gaming, entertainment, which I think there's great value to those applications, but there's also a lot of other applications which I find are exciting for VR. The first category is things that you couldn't experience otherwise, experiences that you wouldn't have access to or wouldn't be able to have if VR didn't exist. So you could put on a VR headset and experience what it's like to be at the International Space Station, for example. VR is great for creating 3D artifacts, giving the spatial reasoning skills that we have. The 3D environment can facilitate that. And then also the third category is learning and education. Here I'm showing an example of manipulating a 3D molecular structure, but there are also a lot of examples of training simulations for surgery, firefighter training, things that would be dangerous to train on physical objects and environments before becoming an expert in it. So these are example VR applications that are very exciting. And if you put on a VR headset today, the visual content that you see is very compelling. The tracking has gotten a lot better. The field of view is better. The resolution of the displays are better. The renderings are higher quality. But when you think about your sense of touch in VR, what happens is at best you're holding a controller like this that vibrates once in a while. So there's really this gap of how much haptic sensations we can render in commercial VR headsets. But when we think about how we interact in the physical world, when we touch a surface, we feel its texture. When we grasp an object, we feel its stiffness, its weight. And all of this facilitates dexterous manipulation, allows us to improvise in our physical interactions with objects. And all of this is currently missing in VR. So if you see some virtual spaceship in front of you and you want to reach out and grasp it, there's really nothing there for you to feel and interact with. So I started off my PhD with this problem in mind, and I was thinking, what if you could, for example, predict what virtual object someone was interested in interacting with? And what if you had a swarm of miniature drones that could move around and kind of puppeteer your haptic interactions with objects? And so imagine you want to interact with this spaceship. What if, as you've reached out to touch that object, these drones moved around your space and either looked for a 3D printed object with the similar geometry, or even an everyday object that resembles the physical properties of the virtual content you want to interact with? So this is what I started thinking about during my PhD. And so I built this virtual experience. Imagine an e-commerce application where you want to touch and feel and you want to purchase this scarf. So current VR applications, when you reach out to touch this object, you can't feel its texture, you can't feel the weight of the material, and these are signals that might inform your decision to whether or not you want to buy that product. So my goal was to use drones as a way to simulate the haptic sensations that you would experience in this case. So I started off with just one drone. We built this custom racing quadcopter, and I wrapped it in a lightweight meshed cage to protect users' fingers from touching the propellers. And then I integrated this in a virtual reality system that I showed you. So we were able to track the drone, we were able to track the user's hand and head, and then we could, once we had a specific area that we could render, we would send those waypoints to the drone, and the drone would autonomously navigate to that point. So I'm going to show you a video of me trying this. So here, when I reach out to touch the fabric, there are different patches of fabric around the drone, so I can feel the texture, and we could also simulate the weight of the hanger that was attached. So as you saw in this video, the position accuracy was not great. The drone was shaking, and this is partially because of all the meshed cage around the drone, but all the fabrics and the weights that we had attached. And we could technically try to improve this position accuracy, but the point here is that all haptic devices have some form of limitation, whether it's a controller you're holding in your hand, whether it's a glove you're wearing, or any category of encounter type haptic devices, which have traditionally been grounded robotic arms, but the drone falls within this category. These all have limitations, whether it's the accuracy, as you saw, of how they're positioned in space, or if it's the resolution of the surface that we can physically render. And you can imagine other limitations like speed and delay of interactions. And the point here is that we could keep making more complicated hardware that are expensive, or we could really take advantage of the fact that our perceptions as humans is limited. So we can leverage the limits of human perception to make these devices work better than they do. So to demonstrate this, I'm going to ask you all to participate in this part of the talk. By touching your two index finger together, you get one chance. No second tries, and you can't look at your fingers when you do it. Okay. I see a lot of kind of crisscrossed fingers. I think some people may have cheated with multiple tries, but I did see those. And the point here is that you're basically relying on your sense of proprioception when you do this. You're using the forces in your arms and muscles to tell you where your finger is in space, and that's a pretty noisy signal. So when you try to estimate where your finger is and touch your fingers together, you're usually not going to be successful because your proprioception, your sense of proprioception is limited. And so that's exactly what I try to leverage in my work. And leveraging these limits can help us make the perception of haptic devices better in VR. So I'll first talk about this project that I mentioned around using drones for haptics, and then I'll talk about another project where we used shape displays for more of a contour following task where you're touching a surface, and we're using this matrix of actuated pins that move up and down to render surfaces. And then in the second half of my talk, I'll shift from haptics in VR to using augmented reality for human-robot interaction and instructing robots, but also using AR to provide explanations for robot instructions. So let's start from the first project. So with the safe-to-touch drone that I showed you, we were able to place different fabrics around the drone. We could attach different 3D printed props, and the drone itself could also act as a box. So it would be a passive prop that could fly and land on different surfaces, and we used it as a shoebox in this virtual reality experience. Before doing this project, I was curious if people would feel comfortable actually touching a drone. And so I ran a study where we had people come to our experiment setup, and we had half of the people, so this was a between subject study design, so half of the people tried to interact with a commercial drone, and the other half of people interacted with an earlier prototype of our safe-to-touch drone. So this was an elicitation study, so we didn't tell people how to interact with the drone. We just gave them an image of the before and after. So for example, one of the tasks was to make the drone take off or land or go further, come closer. And we saw that the group with the regular commercial drone, most of them used gestures and language to control the drone. So they would say things like take off, land, go further, come closer. But the group with the safe-to-touch cage that we attached to the drone, more than half of them physically manipulated the robot. So they picked it up, they pushed it, they grasped it. So this was encouraging that maybe the mesh provides some form of safety measure where people feel comfortable being in close proximity with the drone and interacting with it through touch interactions. So what we wanted in this project was when we had a patch that we could render, we wanted to be able to send that waypoint to the drone and have the drone be precisely where the user would make contact with the virtual object. But what happened in our system was there was sometimes a slight offset, and sometimes the drone also drifted away. And so to address this problem, we took inspiration from a paper from 2016 where they had this kind of magic trick where there were 3 virtual cubes and there was one physical cube in front of the user. And they were able to trick people into thinking that there were 3 physical cubes. So we wanted to basically understand how this worked. And in order to do that, we had to look at how the human brain plans and controls movement. If any of you here are working on robotics, you are very familiar with optimal control theory, but here we're thinking of the human brain as an optimal controller. And what we know is that when you, for example, want to reach out and touch an object like this bottle, your intent is sent to your body. So your brain sends the motor commands to your body, and that results in your arm moving forward. But this is subject to noise and other disruptions in the environment. So the brain has to have a way of understanding what happened, right? So, and it does so by using the sensory signals. And in this case, you visually see your arm moving forward towards the object, but you also feel the forces in your arms and muscles, the proprioception. And these sensory signals get integrated to inform an estimation of where your hand is in space. And the brain uses where it thought your hand would be, and using this difference to kind of update the motor command and allow you to actually reach and have this sort of goal-directed reach motion. So what we did in this project was we tried to think of VR as something that basically intercepts and overwrites these sensory signals. So what we're doing is we're tracking your hand as you're moving close and touching something. And we're transforming this movement to the movements of a virtual rendering. In this case, a virtual avatar. So you can't see your real hand. You can only see your virtual avatar's hand. And what's happening here is you're getting some signals from the physical world. So here you're feeling the forces in your real arm, but you're visually seeing your virtual avatar's hand moving. So this gives us an opportunity to kind of create mismatches and do so in a controlled way. So we proposed this approach that we call dynamic retargeting. And what we do is as the user tries to reach out and touch a fabric, If the drone drifts away to the left, for example, we drift their virtual hand to the right, but ever so slightly and over time. And what happens is that the brain kind of corrects for this, and they end up making contact with the real drone at a slightly different position than their virtual hand is making contact with the virtual fabric. And if this discrepancy is small enough, people don't even notice that they're doing this, and they're very successful at actually touching the fabric, touching the hanger, and making contact with it. And the reason this works is that there are different sensory signals, as I mentioned, so proprioception, but also visual information. So I'm going to ask you all to do the same task again. You get one shot, but do it in front of your eyes so you can look at where your finger is. So try to connect your two fingers together. Was everyone successful? First try, great. That's usually the case, and that's because your sense of vision is more reliable, and the brain knows this. The brain knows that the uncertainty in visual information is lower than proprioception. So when there's a slight mismatch between the two, it relies on what it sees over what it's feeling. And this is known as the visual dominance effect. So we're basically leveraging this understanding of how sensory integration happens to create an interaction that improves the perceived performance of drones used as haptic devices. So we had people come into our lab, we had them go through this virtual shopping experience. Everyone was able to successfully touch the fabrics, pick up the hanger, even though the drone was not perfect and was not perfectly positioned. But we also found some failure cases, specifically when the hand was moving really quickly or if the distance to the target was small, we didn't have enough time to gradually and kind of gracefully offset their virtual hand. And also when the drone was not moving slowly, or if it was moving in different directions, that created a really warped space that was hard for people to navigate, and they started to notice that we were messing with their senses. So in a follow-up project where we were using a tabletop robot for haptics, for example, there was this virtual control panel, and we wanted to have all these buttons and different kind of hardware on the robot. And instead of building the whole virtual panel, we had this tabletop robot that could present the haptic feedback that we wanted. The problem with this robot was that the speed was not ideal. So if someone moved really quickly around the control panel, the robot couldn't keep up. So here, the problem was the speed of the robot, not the accuracy. And what we did was we predicted which button or a piece of the control panel they were interested in interacting with. And to do so, we used the gaze, hand motion, hand speed and direction to predict which item on the control panel they were interested in interacting with. And we were also able to estimate their time of arrival. And we used the minimum jerk model to do this. And the minimum jerk model basically says that in end-to-end goal-directed reach, we tend to try to minimize our derivative of acceleration, or jerk in this case, as we move. So we use that to estimate when we think the user will arrive at the target. And we know the maximum speed of our robot, so we can tell how far the robot can get during that time span. And so we can predict how much retargeting we need to apply in this case. And this helped us to basically decide cases where retargeting made sense, where the discrepancy was small enough, or the distance was far enough, or the hand velocity was low enough, and decide when it didn't make sense to apply this interaction. And sometimes we accepted the fact that there would not be any haptics, or they would be delayed haptic interaction. But that was better than having people have to navigate this really warped space, notice that we were messing with their senses. And so that's the trade-off we made in this follow-up work. So that was the first project where we used this sort of dynamic retargeting, the limits of human perception, to improve the position accuracy of drones used as haptic devices. I'm going to show you another example in the same kind of category where we were using shape displays for haptics. So shape displays are matrices of actuated pins. They move up and down, and they've been historically used in tangible computing, but here we're using them as a haptic device in VR to render different shapes and surfaces. And the problem here is that the shape display that we had was pretty low resolution. And by that, I mean the pins were pretty large. And since then, there have been shape displays with smaller pins, but there's ultimately a limitation because every pin has a motor attached to it. And the more you miniaturize it, the more expensive it gets, or the less force you can apply, depending on the structure. So there's this inherent limitation for affordable shape displays that their resolution is relatively low. So we were trying to address this, and as you can see here, I'm trying to trace this pentagon maze, and my finger gets caught in these pins because of the low resolution. And so we were trying to think of ways to leverage the limits of human perception to make these displays work better as haptic devices. How many of you have used Microsoft Paint? Okay, that's not bad. Usually, I feel like every time I give this talk, there are fewer hands. But if you remember Microsoft Paint, when you drew a line at an angle, there was a kind of a rasterization problem where it would be very pixelated. So this was exactly the problem with the shape display that we had. So it was kind of a physical rasterization problem where, because of the low resolution, the pins, it would be hard to trace the surface. My fingers would get caught in these pins. And so we were trying to think what is an equivalent of an anti-aliasing in this case. And what we decided to do was that we rendered a horizontal line, and we would, again, use the same kind of redirection illusion where we would shift the user's finger upwards. So the brain corrects for that movement by going down. So visually, they're still following a line at an angle, but physically, they're following a horizontal line. And this helped basically make the interaction much more smoother. The line that they were following was straight. And so we were interested to figure out how far could we push this illusion. And by that, I mean, if you try to follow a line at a very large angle, you will expect certain forces in your finger and wrist. And so we were wondering how far we could take this illusion before people noticed that we were messing with their senses. So to do so, we ran a study. We used a method of constant stimuli where people experienced multiple repeated samples of different angles, some of which had no illusion. So the virtual line matched the physical line they were tracing. And some of them, they were tracing a horizontal line, but visually they were following a line at an angle. And so this is a classic kind of psychophysics test. And the results we got is also kind of a psychometric curve that's S-shaped. So the x-axis here is the angle distortions that we tried. So we tried 5, 15, 25, 35, and 45. And the y-axis is the ratio of repeated samples that one individual in our study noticed that we were applying an illusion. So the conservative detection threshold here is 50%. It's the point where people half the time say, yes, there was an illusion, and half the time they say no. So this is a point where people are just noticing that we're doing something fishy. And then by 75%, this is usually used in psychophysics tests as the detection threshold, where most people, most of the time can tell that we're kind of applying some sort of remapping to their movements. And we found in the case of our display, given the dimensions and the length of our display, we could do this up to around 49.5 degrees. So after that, around 50 degrees is where people really expected the forces in their arms to, and were able to tell that they were not following a line at an angle. So we wanted to then see if we stuck below these angles, would that actually help improve users' experience with this haptic device? So we ran a follow-up study. We didn't tell people, this was a new set of participants. We didn't tell them anything about an illusion. We told them that we had 2 different shape displays. And because they were in VR, we could do that because they couldn't actually see the shape display. But we only really had 1 shape display. So what we did was we used the method of 2 alternative force choice tasks. So half the time, they basically experienced 2 shape displays at once. and we would ask them which one they preferred, which one they thought was smoother and higher resolution. And these are the results that we got for 40 degrees, which is the highest angle below the detection threshold that we tried. This is aggregated across all of our participants and also across all the repeated samples. And we saw that in majority of cases, people thought that the case with the illusion, so the shape display that we had with the illusion, was higher resolution, smoother, and the one they preferred, even though they were both the same shape display. And we also found the same results for the other angles that we tried, like 10, 20, and 30. So this was encouraging that maybe applying these types of redirection illusions could help improve the performance of shape displays when used as haptic devices. We also tried a few other methods. I'm just going to give you one more example. Here, I'm rendering a semisphere on the shape display. So you can see that there are only a few pins in that area. And there is the elevation change is pretty drastic. And so what we do instead is we kind of scale up the rendering on the shape display. And we change the user's speed of their finger as they're tracing the surface. So if any of you are familiar with the control to display ratio on the computer mouse and the cursor, this is basically applying a CD ratio gain to your fingers as you're tracing the surface. And so what this allows us to do is we can have smoother surfaces, we can render more details, even though we have the same low resolution shape display. I won't go into the details of the study, but we did the same kind of psychophysics test. We found that we could scale up the rendering by almost 2 times on our shape display, given the dimensions that we had. And we found enough follow-up study that actually helped improve the smoothness and resolution of the renderings, and also it was what people preferred. So in the second project, I showed you 2 examples of techniques we used that leverage the limits of human perception to make a relatively simple and affordable shape display work better than it actually did. So the first half of my talk has been focused on using drones and shape display for haptics and using these perceptual illusions to improve their performance in virtual reality. In the second half, I would like to talk about kind of continuous work that we've done since then, and more recently on object-oriented interactions for human-robot interaction in physical spaces. So the first project I'll talk about brings some of these ideas of perceptual illusions to physical spaces. And the goal here is to use robots to extend people's abilities in physical space. So the goal that we had for this project was, what if you could reach out and touch and grasp an object that was far away from you and bring it to you? And so there's a traditional interaction design in VR called the go-go interaction, where your virtual avatar's arm can grow really long and grasp far objects. And so we wanted to bring that to the physical space, and we call this reality go-go. So here in this video, as you can see, you can reach out and you can grasp a far object, and we're instantly deleting the original object and giving you a virtual duplicate, virtual twin in your hand that then you can place on any surface. So even though you're not that's not a real object, it creates this illusion that you're instantly grasping far objects and bringing it close. And you can imagine this doesn't have to be something physical that's in your space. It can be something you're buying online, or some object in your fridge that you can access through a menu, or even like objects in other rooms in your house. So you could look around and pick an object, let's say this coconut water, and place it on the surface. And what we call this is reality promises. And basically, we're thinking of this as, once you perform this interaction, you're creating a reality promise. And this is work done by my postdoc, Mo Kari, that was presented at WIST conference 2 weeks ago. And the idea that we wanted to realize with this project was, how can we fulfill this reality promise so that when I reach out, there's not just thin air when I touch this object, but this is also not something that I care to have haptic force feedback or tactile sensations for, because if you see a virtual Pringles or coconut water, it doesn't matter if you can feel the bottle. You want to be able to consume the coconut water or the chips. So it matters that that object is in a physical form, not just a haptic rendering. So to make this happen, we create this idea of reality promise. We use this kind of rendering to show the progress, and we have a time estimate of how long we think it would take for the object to be materialized. And you can continue to do whatever virtual task or a real task you're doing. And after a few seconds, your object is a physical coconut water that you can sip from. So I'm going to show you behind the scenes of how this works. So this is Mo in my office. And basically, the idea is that we create these reality promises in a physical space using augmented reality, pass-through augmented reality. And we have this invisible robot that basically fulfills the reality by performing the physical interactions. So I'm going to briefly talk about how we actually make this happen. So our system basically has two components. The first one is the interaction synchronized robot control that we have. And so we have a headset on the robot so that we can have bidirectional communication between the user and the robot. And we can track where the robot is, but also the robot knows where the user is. And we can send the instructions based on user interactions so that when the user moves one virtual copy of an object over, those we can compute the grasp pose, but also the base position, and send that information to the robot to perform. And what this enables is also that we can predict roughly how long it would take, and that informs the progress bar and the time estimate on the object. The second piece of our system is the Gaussian splat rendering that we are using on headset. And so here you can see we used a regular iPhone to scan my office, and this is a rendering on headset using Gaussian splatting. And what we can do with this is we can have this sort of cone of reality that basically we're rendering on top of the pass-through augmented reality scene. And here you can see Mo can kind of delete Lauren from view, or in this case, because we know the position of the robot, we can cast a cone from the user's headset so that we only render the points from behind the robot in front of it. And so regardless of where the robot is moving or where the user is moving, we can kind of delete the robot from view, and then we feather the results to make it more transition better. Obviously, this is not perfect, but you can get the idea, and with improved Gaussian splat rendering and better color matching, this will become much better in the future as well. So with this approach, also a quick shout out that my PhD student, Cyrus, is releasing a Gaussian splatting toolkit very soon. So if you're interested in doing any of these things yourself in an AR or VR headset, stay tuned for this. This will come out. So everything is rendered on the headset. You don't need a powerful gaming PC. There's no streaming. And also his toolkit has all sorts of building blocks to make these interactions really simple. Oh, I'm supposed to play this video, but yes. I can also repeat. No worries.
So I really like this idea. It's very interesting. But a couple of questions on this. Like the first one is, why is this better than just using speech? Say, hey, robot, bring me the coconut water.
Right. Yeah, that's a great question. So I think of it in a few ways. One is this the same reason we have direct manipulation interfaces. So on the computer, we used to use the terminal, we used to type in, open the folder, and now we drag and drop folders, right? So direct manipulation in general has advantages in scenarios you don't have to speak. But the more interesting thing to me is that there are scenarios where the spatial parameters are important. So I guess not in the case of the coconut water, but I can imagine if I'm building a structure with a robot, I want pieces to be placed at an exact position and orientation. And that's really hard to describe with voice alone. Whereas if you just grab a virtual copy and place it, you can specify the position and orientation very quickly. So I think I don't think of them as better than the other. I just think of them as complementary interactions that might be suitable in different scenarios.
Understood. And the second question is, why removing the robot from the visual feed of the human? Right? Maybe you don't want that the human collides with the robot.
That's a great question. So I think of this project as having two pieces. The first one is we're removing the physical object and giving you this virtual copy. So that piece, we're using the same technique as removing the robots. And that piece to me is the exciting part. It's what can extend people's abilities and give them this power in the physical space that they couldn't have otherwise. The making the robot invisible is kind of, to me, a side endeavor that maybe is not central to what we're doing. And you can imagine you could see the robot do this, but it wouldn't create this illusion that you were manipulating physical reality instantly. Because then you would see the robot bring the object, whereas here, we're blending the kind of boundary between virtual and physical so that it's a seamless interaction. I can see some examples of like if you have a small apartment, you may not want to see the robot, and maybe that's advantageous in some ways, but here it's more about the instantaneous interactions and creating this illusion that people are actually manipulating physical space. But I don't think it's necessary to remove the robot all the time. But we do have, we could add obstacle avoidance to the robot and things like that, and yes. And I'll talk about, the next project I'll talk about is exactly what you're saying, where we're not deleting the robot, but using this interaction paradigm while seeing the robot.
It's a fascinating concept. I'm wondering whether this could also be extended sort of beyond line of sight. If you wanted to like fetch pills in another room.
Right. Yeah. So I think the menu with the coconut water is exactly what we were going for with this, where you could have a menu of items that you bring, and it could be in a different room. Or you can imagine you could have a world in miniature in your hand of your house, and you could just bring things from that to the space. Yeah.
How much delay can you tolerate?
Yeah, that's a good question. So
I tried this 20 years ago.
okay.
Two dancers, one in Berkeley and one in Illinois, danced together.
Oh, wow.
But the big problem was to manage the delay.
Ah, okay.
Just couldn't get faster to it.
Oh, that's a
So that they feel, the movement of the other.
right. That's a great question. So I think the delay here, so we call it a reality promise because there's almost like a split of what's happening visually and what's happening physically. And the goal of the robot is to basically catch up reality to what the user visually sees. So the delay is not so much about the synchronization of the movements, but it's more about the physical act of the robot grasping something and bring it to you. And we try to use this countdown and the animation to communicate that there will be a delay so that people don't expect that when they grab an object, there's something there. But what you're describing is more when you have a remote robot or operator. And so that depends on the lag between the connection, and that's not an issue we had in this case because the robot and the user were co-located in the same physical space. But I would say things have gotten a lot better. Even from the first project I shared, you can see the rendering quality has gone up a lot in the past 8 to 10 years. and same with the lag and other aspects. Great, so putting everything together, here you can reach out and grab an object. In this interaction, we're not deleting the original, we're keeping a duplicate. We call this the dematerialization and rematerialization interaction. And what's nice is that we can predict which surfaces the robot can place the object in and allow the user to only place the object on those surfaces. And so we can, once the object is dropped, the robot kind of catches up the reality of the user, what they visually see and what's physically happening. So the physical cause is the robot doing this, but you can imagine the virtual cause can be different things. Here, it's the reality go-go or reaching out to touch something, but you can imagine there could be a virtual character that can actually have physical effects in the space. And the trajectories we create draws the user's attention away from the robot so that when the character drops the chip, you can actually reach out and eat it. So for those of you who are not from the HCI community, this is kind of a famous quote that we often reference from Mark Weiser, which says, "The most profound technologies are those that disappear. They weave themselves into the fabric of everyday life until they're indistinguishable from it." And we took this very literally in the project that I showed you, and the robot is the technology that we're literally rendering invisible. But as you mentioned, there's no reason the robot needs to be invisible. That creates that magical interaction. But really what we're talking about here is that we can shift the interactions from interacting with the robot to interacting with objects. And I think that has interesting properties that we could leverage, for example, to provide explanations for what robots are capable of doing or what the boundaries of their limitations are. So the first half of my talk was in virtual reality. So we had these VR headsets. Then I talked about reality promises, which was in pass-through augmented reality. And that allowed us to basically be in control of every pixel of the interface and delete objects. But you can imagine having more lightweight form factors with AR displays that are see-through, optical see-through. So you can render objects, but you can't necessarily delete everything. And even with these devices that are lightweight, we can have these sorts of object-oriented interactions for robot instruction. So here's my PhD student, Lauren. You can do a lasso selection, select a bunch of objects, and then you grasp them and move them to their default position as a way of quickly instructing the robot. And as you mentioned, I could just say, put stuff back on the shelf, or I could do this very quickly, and the robot could come and fulfill those instructions. But what's more interesting to me is that this sort of direct manipulation of what we call ghost objects, so these virtual twins of objects that are at lower opacity, allow us to not only communicate the affordances of the robot, given the robot's capabilities, but also the limitations of what can't be done. So here in this shelf, maybe I can grab one of the boxes off the shelf, but some of them are too high to reach, or some of them are too low to grasp given the mobile robot that I have access to. So in this project that's very recent, currently we've submitted it to HRI, the Conference on Human-Robot Interaction. This is what we work on and try to use these sorts of object-oriented interactions in AR to communicate robot capabilities and limitations. So what Lauren worked on here was, oh, did I forget to put her? I forgot to put her face, but I'll point her out at the end in my slide. But what she worked on here was that we have the headset, so we can create a scan of the environment. And we also have information about the robot. And she used the VLM to basically create a data set of all the objects and their properties in the environment. And she also has a 3D mesh of the entire scene and all the objects. And we use that to basically create these interactions and send instructions to the robot. So I'm going to show you a few examples that Lauren recorded. So this is an example of the shelves. So she can see which objects the robot can grasp using this ray and dot. and she can grasp the duplicate ghost object and move them around to instruct the robot where to place them. And in real time, if she goes too high, she gets a message that the robot can't reach that position. And once the instructions are done, she can send the commands to the robot. And then we then send the poses and instructions to the robot. So at no point in this interaction, the user is interacting with the robot directly. Everything is done through these object-oriented manipulations. Here's another example where you can manipulate multiple objects at once. So here she's doing a lasso selection. She gets 3 virtual copies and they snap to default position. But then the interesting part here is that the user and the robot can kind of engage in this sort of mixed initiative approach for resolving when things arise. Sometimes the human helps physically, sometimes they can help virtually, and sometimes the robot might suggest alternatives in the process. Maybe I'll skip all the robot actions. Yes.
I had a question in terms of like, how do you determine which items you're Thank you for giving this talk, by the way. I had a question on kind of like your lasso effect. You're taking like the objects on top of the table or on top of like a chair. Is there like a locking effect for certain items in the room versus not? Or
Okay.
how do you like interact? Like maybe I do want to move that chair eventually.
Yeah, that's a great point. So you can look up the paper called Ghost Objects. It's a short poster that Lauren presented at the WIST conference 2 weeks ago, just on that interaction of how we enable lasso selection of physical objects. And so there are some heuristics we used. For example, if the entire object is intersecting with the cone or the 3D geometry from the ray, then we include it in the selection. But if it's not fully enclosed, we don't. So you could technically select the chair and it will turn red and tell you that the robot can't pick it up because it's too heavy, for example. This is the last example that I'll show, and it kind of demonstrates higher levels of abstraction than just pick and place. So the first one was a single object pick and place. The second one was multiple objects. And the third one is if you select, for example, the curtains, you see higher abstraction levels like dim, brighten, and draw. And the robot can't reach the one of the actions, but it can draw the curtains, and so Lauren can specify spatially how far she wants the curtain to go up to, and this would be difficult to describe with words, but very easy to do with direct manipulation. And so once she sends the commands to the robot can pull the curtain up to where it was specified. So this is an kind of line of work where we're using these sorts of object-oriented interactions in AR for not only instructing robots, but kind of exposing what are the action possibilities, what are the limitations, and allowing people and robots to work together. So ways we want to extend this work is we want to have other simulations than these kind of static constraints we currently have, like the reachability of the robot or the graspability of objects. And we want to do more real-time simulations of what, once the instruction is done, whether or not we predict the robot would be able to execute that action. We want to also extend this to real-time reconstruction. So recently Meta released some toolkit for creating the 3D mesh from the pass-through cameras themselves. Here we have a capture of the environment that we've done beforehand. And so this will allow us to do real-time reconstruction, but also track the physical space as things move around so that we don't have the static representation. And I think that would be an interesting domain for things like teleoperating the robot, where the user can be in, let's say, a virtual environment duplicate of a real world scene, and they can just manipulate ghost copies of these objects and see the physical actions as the robot moves around. And so we can use the view from the robot's vantage point to make these sorts of teleoperations happen. Some areas that if any of you here are interested in is out of my expertise, but I would be curious if there are opportunities for robot learning here. Specifically, if we could, for example, limit the possibilities of movements to the plausible trajectories, maybe we could learn about users' preferences of how they want things to be done using these interaction paradigms. So today I talked to you about using drones and shape displays for haptics in virtual reality, and using this sort of object-oriented interactions in AR to instruct robots, but also communicate robot capabilities and limitations. So there was a question earlier about why do we need to interact with objects? And so to me, this is just one interaction paradigm that sometimes might be useful. But in my group, we're also thinking of, we don't necessarily need to have the drone, the robot be invisible, or we don't necessarily always want to directly manipulate virtual objects. We could even have glasses that have cameras, but perhaps no visual display, and we still could have interesting interactions. And this, there are some work in my lab that were very early stage, but I just wanted to briefly mention in case anyone was interested. So in the two projects that I will share briefly, we assume that the user is wearing glasses that have cameras, so egocentric RGB view, but there's no display. So everything's done through other modalities. So in the first project, our goal was to understand human intent in instruction beyond just language. So can we understand people's gestures as they communicate? And a lot of human-robot interaction research focuses purely on pointing. And so we wanted to go beyond pointing and look at other gestures. So what we did was we brought two people to our lab. So we had pairs of participants come in, and someone was instructing another person in a different room how to build these Lego towers. And they couldn't see each other. They could only hear each other and see their 3D hands of the instructor. And so now we have this data set of speech and 3D hand gestures of humans instructing another human, but could be another robot, of how they could build what they want to build basically with Legos. And I'm going to share a few results from our study. So let's say you want to build this C-shaped tower. What we found was that over time, so we had people do this 12 repetitions, different towers. What we found is that over time, people's language became more ambiguous, and they used complementary gestures to fill in the gaps. So instead of saying, put the block on the left side and kind of moving an imaginary block to the left side of the grid, they would say pointing this way. And if you only listen to the language, there's not enough information to execute this action. So the information about the position and orientation is actually encoded in the gesture. But we also saw things beyond just pointing. Over time, people developed conventions with each other. So they would call this tower the C-shaped tower. And the next time around, they would say, put the tower like this. And people knew that that C-shaped hand gesture meant this green block, red block, and green block. And this is something that I think is interesting, is that as humans, the more we collaborate with each other, we develop these gestural and linguistic conventions to become more efficient over time. But current systems, we think of these like predefined interaction paradigms that remain rigid over time. So there are opportunities here for agents that can be convention aware, both understanding when people kind of come up with these conventions, but also perhaps proposing them themselves. A second project I want to briefly mention is done by Beza. What we did was we manually annotated the HoloAssist dataset, which is a dataset of egocentric views recorded by Microsoft, where people build different IKEA furnitures or do other sorts of kind of physical tasks and assemblies and repairs. And there's an instructor somewhere else that can interrupt and tell them when they're doing something wrong or tell them some proactive instructions. So we were interested in what motivates an instructor to interrupt and proactively give instructions when someone's not making a mistake, they haven't paused. And we kind of looked at the 10 seconds before an instructor's interruption, and we found interesting patterns where if the user was doing any sort of repeated interaction, repeated rotation, shifting, or we actually categorize a range of cues that we think instructors use to decide when a human is uncertain or needs help. And our goal is to now, we're working on building methods to detect these instances so we can help people when they struggle with a task. So we're thinking of this for AR mainly, where we can show the instruction in augmented reality, but you can imagine if you have a robot, it could come and help you with the task if it can detect that you're unsure of what to do or you're struggling to complete the task by yourself. So these are two examples of kind of thinking about input, both explicit user input, but also implicit behaviors that can shape how we design robots and human-robot interactions. So with that, I want to kind of summarize with what I think the field of human-computer interaction can contribute to the space. So if we think about the 60s, we had mainframe computers and personal computers. As I mentioned, we were using the command line interface. And Doug Engelbart and others at SRI developed the computer mouse, and then we had the graphical user interface in Xerox PARC, where we used the metaphors that people were familiar with, like desktop and folders, to allow people who didn't have a technical background to interact with computers. And this helped us bring computers, personal computers, to people's homes in a lot of contexts. In the 90s, Mark Weiser, whom I quoted earlier, is one of the kind of widely regarded as founding people who founded the idea of ubiquitous computing, devices of different sizes that we carry with ourselves everywhere. And we worked on using gestures and touch gestures and other things to allow people to more effectively interact with these devices. So what I think about in my group is that as computing is becoming more distributed and situated in our physical spaces, and as we have these wearable devices, what is kind of the next generation of interaction that can allow these devices to coexist with us in our physical space, so that not everything is automated, but we can actually understand user needs and allow this sort of bidirectional symbiosis between devices and people. So with that, I would like to thank my students and collaborators whose projects I mentioned today. I forgot to put Lauren's face on the OHRI paper, but she was the PhD student who worked on that. And with that, I'm happy to answer any questions.
We've now got time until around 11:40 or so for questions for Parastoo. So feel free to volunteer a question and I can bring the microphone to you. One question to get us started, Parastoo. So really cool vision of like future computer-enabled realities. You showed a few examples of different scenarios where people might want to reorient their environments and summon certain materials and stuff. I wondered if you could just talk about the things that are most personally resonant about you if we were to have these activated workspaces that worked up to kind of the eventual vision in 10 or 20 years. What do you think are going to be some of the most impactful ways that it would change the way that we worked with our spaces?
Yeah, that's a great question. I think about that vision as something that can extend our abilities so that we can do more faster. And I guess that's one area where if, for example, I could easily rearrange all my furniture, see visually what it looks like, see what I finally like, and then just have robots kind of figure it out and do all that, then I can go do my cognitively demanding tasks that I'm excited about and be creative and do my own thing. So I think of it as a way of extending people's abilities and in the physical spaces. I don't know if that answered your question.
Amazing talk. Thank you so much. I want to ask you so many questions, but you talked about just a moment ago about extending people's abilities, and I'm wondering if you've thought about like assisted living. I could imagine this being extremely helpful in like nursing homes or in places where people are, need additional help with things we take for granted. And I was curious if you've thought about that as a use case.
Yeah, that's a great question. Yeah, there's definitely that's not something we worked on in the paper, but when we posted the YouTube video, some of the comments were people who had upper motor disabilities, and they were excited about the potential future where we all could have these super powers to reach out and manipulate far objects without without having to physically move there. I would be curious how this could be used as a assistive technology, and would be open to collaborating with folks who work in that space. And similarly with the visio-haptic illusions, there's existing work on using those for rehabilitation, and people have looked at how these illusions, when you, for example, move your arm, if you can, in VR, if you exaggerate people's movements, people sometimes feel a sense of progress, and they end up having a wider range of mobility. That's also not something I've worked on, but there's research in that space as well.
Thank you.
Hello again. I had a question. So, for example, when I'm guessing that you have like the extended idea that maybe I have a dirty room and I have positions for all the objects in the room where they should be, right? Obviously, some of them might be in a position that you can't, like the robot can't physically get them. So, how do you have like any ideas of how the robot's going to, or like your system's going to interact with the human? Say like, oh, maybe if you just move the book a little bit over here, then I could finish the task.
Right. Yeah, that's a great point. And so we basically in the yeah, that's really what our goal is here, is to both have these default positions where people can have efficient interactions, but also give them the flexibility. You don't have to snap to default. You can always place things at different places. And in the paper, we talk about this mixed initiative paradigm where when things don't work, like here, when the robot can't put the blocks back in the basket because of the table, you see this menu that shows up that basically gives options. Oh, I went to the next one. But the menu basically says auto, alternative, or ignore. And so those are kind of the paradigms that we want to allow people to interact with. And so if you pick alternative, we try to find, for example, if you're looking for a cup that's 2 up, we give you an alternative cup that's lower and highlight that as an object you could, for example, pick up, or give alternatives where you could either move other objects to make room, or other placement options for the robot. We did a study, which we also talk about in the paper, where we saw that people also physically help the robot sometimes. So if the robot, for example, we had a Roomba style vacuum cleaner, and that was in a different room, but the door was closed. And so people would open the door so it could come in. So the goal is to expose these like limitations in ways that people could either virtually resolve it, use the system for some sort of a suggestion, or physically help the robot when it needs it. That's a great question.
Thank you.
We got time for one more question. So one more question from me. You presented a lot of really cool work around reality distortion, and you have in your curves a certain point at which people start to realize that a trick is being played on them. I wondered if you could talk a little bit about the costs of someone realizing that there's a trick
Ah.
played on them with reality. Like if you flub it every now and then and are over aggressive, is this a cool thing? This is like totally not a cool thing. I'm
Yeah.
just curious what you see when
Yeah,
you do
that's
things like
that's
this.
a great question. So I have a totally different talk on this topic that doesn't use robots per se, but basically all of these remappings, it's a continuum. So there's a point at which people notice that you're messing with their senses, and then there's a point where they are aware that there's a remapping, but they can learn and adapt in many cases. And so some of my work tries to leverage this plasticity in our brain and our ability to adapt to remappings to do things. And I think partially this idea of, like, for example, your arm growing 2 times as much and for you to grab an object, that's a remapping that we're not used to or we're not familiar with. We definitely notice that it's happening, especially past a certain point. And so there's research studying what's like the length of the arm that people can adapt to, and what is the length of the arm that, for example, is too much for us to learn. And what's interesting is there's also after effects. So if you learn to operate in a really warped space, when you take the headset off, you're going to struggle to reach and touch things. So you have to think about, how do we undo it before people come out of these virtual spaces so that they can immediately continue their interactions in physical space. And then the other point to mention is the thresholds. As you saw in these graphs, the error bars were really large, and that's because people are very different. So me as a computer scientist sitting at my computer all day have a very different sense of proprioception than a ballerina. And so it's important to notice these moments where someone is consciously relearning and remapping their movements for different people and adapt to individual differences that way.
Thanks. Let's all give Parastoo a round of applause for today's talk.